So you're out in your boat and you're crashing through the water at 3 meters per second. You're moving to the east at 3 meters per second across a 300-meter wide river that is raging downstream at 4 meters per second. Now recognize this is a fast-moving river, and you are nearly as fast in your kayak pushing across this water. But let's ask, is this water coming down at 4 meters per second slowing you down, or just carrying you downstream while every second you still get 3 meters closer to the opposite bank? Well, that's it, isn't it? You're moving at 3 meters per second east across the river, so that will get you down the river. My dog doesn't think that's a good idea for you to be doing that, but you gotta do it anyway. Thank you, Kaya. So, the 4 meter per second river speed doesn't slow you down at all. It simply carries you downstream. You are, in fact, moving at 3 meters per second across a river that's 300 meters wide. Think, how long will it take you to get across that river? 3 meters per second to cross 300 meters. Did you come up with 100 seconds? You're very good. All right, so if you're on this water for 100 seconds, and each second you're carried downstream at 4 meters per second, how far down the river will you be carried? In 100 seconds, you'll be carried 400 meters. That's exactly correct. So we're going to work that problem out in river problems. And the last thing we're going to work out, we're going to need our trusty calculator to work out exactly what your true course and speed will be. So the standard questions are always, how long to cross? And we already came up with it's going to take us 100 seconds, but we have to do this formally. So we write givens, underline it, our velocity. Well, our velocity in which direction? So under here we might write in subscript across. Givens across. Only the givens that get us across here or pertain to that are going to go down here. So our velocity then is clearly 3 meters per second. The distance we are crossing, well, that's right here. That's the distance across the river. That is 300 meters. And then the only remaining question is, how long is that going to take? And we put a big question mark for that. So what is our formula then? Is there an acceleration here? Always ask, is there any acceleration? Well, what's a free body diagram on the boat look like? While the boat is being pushed by forces, the boat is moving at constant velocity in both this direction and this direction, so a free body diagram would have no net force remaining on it. So the formula is V equals D over T, our very first formula. And we're looking to solve for T, and we know that we could just swap these two guys here. Sort of algebraic magic. Don't tell anybody I told you. D over V. Are we helpless, though? If this was stupid magic and we got this wrong, are we helpless because we messed up on the formula? Is that where we're at? I hope you realize we are not there. T equals D over V. So what's the distance? 300 meters. The velocity is 300 meters per second. Well, when we divide, we get 100, but 100 what? Because if the units don't work out, we, in fact, messed up on the algebra, and we don't want to mess up on the algebra. So I got rid of the meters per second here by multiplying by seconds over meter. That's the invert and multiply thing. So up top, inverting and multiplying, the meters cancel. I'm left with seconds in the numerator, which is just where I want it. So 100 seconds, that lets us know our algebra was good all along, and we did smart physics. So now we have givens, and what would we call this? Well, we call this down. All right, we're just going to talk about the things that are going down. And we know the velocity down is 4 meters per second. And we know the time that we're on the river is 100 seconds. And we want to know what the distance that we will be carried downstream. So the formula, again, we start with velocity equals distance over time. We're solving this for distance, and we do that with multiplication by time by both sides. So d equals velocity times time. And again, we'll check that to make sure that the units work. So distance equals velocity times time equals 4 meters per second times 100 seconds. And we see the seconds nicely cancel out there, leaving us meters. We're looking for distance. So that sounds like we have found the right formula indeed, 400 meters down. So that's how you do river problems. That's the first two questions, the second question being how far down. And the third question is always, what is the true course and speed? Now, true course, what do we mean by true course? Well, that refers to our navigation system here on planet Earth, where north is 0 degrees, east is 90 degrees, south is 180 degrees, and west is 270 degrees. So that would be true course. So we want to plot it on this. So we'll make our triangle, but then we'll refer our triangle back to this, which fortunately is the same as the xy axis anyway. So we have two vectors. We're going to add them tip to tail. So we have 3 meters per second and 4 meters per second, and scale this appropriately. And here's the resultant then. And if you know your triangles, you know this is a 3, 4, or 5 triangle, so that's 5 meters per second. And if it was anything else, how would we calculate it? Well, we'd use Pythagorean theorem, of course, to calculate the magnitude of this. And we have to use trigonometry, of course, to find out how big that angle is and which trig function are we going to use. Well, these are givens, so these are much better data to use than the 5 meters per second. So we would use the tangent function so that we're using the opposite and adjacent legs. So we would go tangent of theta equals opposite, which is 4 meters per second, over adjacent 3 meters per second. What does that equal? Well, we need a calculator for this one. So 4 divided by 3 equals, and press second tangent, and I get 53 degrees. So good to remind us exactly what we got here. All right, so this is our eastward motion, this is our southward motion, and so this is 53 degrees, but that's not our true course, because 53 degrees would be something like that there. So when we plot this back on our compass with 0 degrees here and 90 degrees here, we see this is a rotation of 53 degrees more than 90 degrees. So it would be 90 degrees plus 53 degrees, which is 143 degrees. So what we would have is 5 meters per second at 143 degrees. And that would give us the answer to what is the true course and speed. So that's how you do river problems. They're kind of fun. It's important to remember there is no acceleration going on here. So our formula is simply velocity equals distance over time in every case. That is the special feature about river problems. It's two vectors combining, and we're always combining them here in a simple way, just at right angles to find their resultant vector, and always at a constant velocity. Thanks for watching.